Hello and welcome back to Calculus 1. We are starting chapter 4, application of derivatives. And the first concept that we are going to learn is minimum and maximum of a function, or minima and maxima. So you can have many of those. They are classified as local and absolute or global. We'll talk about the classification as well. So generally, and for our application, which we are going to explore further in, I believe, 4.4, generally we like to know where a function has its maximum and has its minimum. So, yeah. If you observe a curve, f of x, like this, we see that that curve has a max point, right? Which has the coordinates, let's say, a f of a. And in this case, there are no higher points than that point, and that point would be considered as absolute max or global max. We can have this situation where, again, you have a max and another max. So in this case, you have two. Now, this one over here is called relative, also known as local. And this one is absolute or global. So those are the words that we use. It shouldn't take too much brain power to realize that the absolute maximum is absolutely highest point on the graph in terms of the y value, and the relative or local max is max in its own neighborhood. So you can think of I don't know, president of the country and mayor of the, or governor of a state. All right. So governor of the state is the boss in his state, where the, or her state, where the president is in charge, right, globally, and that's the top. So what happens, and you have the same situation for min. But I need to also mention this type of a graph, where this shoots to positive infinity. This guy over here is also a max. Now, what do you think? What kind of max would this one be? Global or relative? Relative. There are, as you can see, all of these points here are higher than the max that we have, so that has to be the relative max. So now you have these three graphs, and you just flip them upside down for minimum values, and you have relative minimum, relative maximum, sorry, relative minimum and global minimum, and so on. So if I draw, let's see, yeah. Over here, so this goes to infinities, right, up. So this one over here is relative, also known as local min, and this is absolute, also known as global min. Now, as you can see that this one goes to negative infinity, this one over here is relative min. So use your eyes and common sense, and you should be good to see them on the graph. But we also want to figure this out using calculation. Now, what is interesting over here is to note that tangent lines at each one of these, whether it's a min or a max, local or global, all of the tangent lines you draw through these are horizontal, and their slope is 0. All the horizontal lines have 0 slopes. And if they have 0 slopes, that means that the derivative equals 0 is the one in charge to find the locations where these occur. So we're going to first define something that is called the critical point, and then we're going to define figure out the procedure to find minima and maxima of a function. So a critical point so this is the definition now. An interior point C of the domain of F at which f prime of C is 0 or f prime of C does not exist is called a critical point of F. Now, I don't really like the fact that they say C is point. C is not a point. C is a coordinate of the point. C, f of C, is a point. This is actually a critical number. This book doesn't really distinguish well between those. So what we do, if you are learning over here, you have two separate ways to get critical number. So derivative is equal to 0 or derivative does not exist. And then at that point, when you find all of those values, critical numbers, some of those will be points and some of those points will be min and the max. So let's figure out cases. You have to be very careful with these types of analysis, and you have to think and you have to pay attention. Otherwise, you are going to write some nonsense that will make no sense whatsoever. For instance, if we start with f of x equal x squared, to find critical number, we take the derivative, which is 2x, and we set that equal to 0. We obtain x equals 0. Then we find the y value for it, which is you plug the critical number into original equation. So 0 squared is 0. And finally, we have 0, 0, and that's your critical point. Now, we know for x squared, which is a parabola, that you have that minimum at 0, 0. That was easy, right? Because we already know. But we show the calculus way analysis to calculate 0, 0 using derivatives and so on. So the way it's done, we use the definition above. We set the derivative equal to 0. We solve that equation, divide both sides by 2, right? And we have the critical number. We take the critical number, which is only the x coordinate, plug in the original equation to get the y, and now you have x and a y, which is 0, 0, and there was this puppy here. Now, we know the way x squared looks like, right? We know what it looks like, and we know that in this case it's a minimum. Will this procedure work like this all the time? The answer is no. it will work out most of the time. I will immediately give you an example where not thinking can get you in trouble. F of x equals to x cubed. The first derivative there is 3x squared. When you set that equal to 0, you get x squared divided by 0 over 3 is still 0, and you get again x equal to 0. And again you get y, which is f of 0, to be 0 cubed, which is 0, and there's your 0, 0 again. It's still a critical point because it satisfied the definition. Is it a min or a max? Hell no, right? It's going to be something that we'll learn later called inflection point. As you can see, the cubic graph has the squiggle right there at 0, 0, and it's not min or a max. So you have to be careful. You detect min and you detect a lot of critical points solving these things, but not all of them will give you right. Let's think about does not. So I'll put here 0, 0, not min, not max. So obviously we have to learn more stuff, and that's coming up in future lectures. Another case. F of x equals absolute x. Have to differentiate this. Now, the way to differentiate this is to write its definition. And now when you differentiate each one of the pieces in the piecewise function, we come up with a derivative that it's simply 1 and negative 1. Now we've seen this before, right? So we know that the original function graphs this way, and we know that the derivative graphs like this. So here, I'll write in blood, the derivative at x equals 0 does not exist, which means x equals 0 is critical point. And you know what? Yay! It's a minimum, right? You can see that using your eyes. There's the minimum right there. It's the absolute minimum for the function. The derivative value did not exist, but our definition allows for it to have a minimum if the derivative doesn't exist. So now we have that x is equal to 0, y is equal to f of 0, which is absolute of 0, which is still 0, and it spits out 0, 0 point. And 0, 0 point in this case was a critical point, which was a minimum. So here is the case where the derivative does not exist and it's a minimum. And finally, have one more. F of x equals 1 over x. The derivative of this one is negative 1 over x squared. What's happening here at 0? If I set this equal to 0, what happens? We get negative 1 equal to 0. No solution. We know there's a vertical asymptote at x equals 0. When there is no solution, means no critical point, which means no min-max. You can have that situation. And again, if you remembered your basic functions, when you draw 1 over x, it is clear there are no min and max values on this particular graph. So now you've seen it all. You've seen a problem where calculation clearly gives you min or a max. And most of the time, it's that type of a problem. X cubed gives you a false positive. Let's call it that way, right? This one you have to detect with a different calculation that we are learning in the next lecture. You also have a situation where the derivative at the point doesn't exist. And when the derivative at the point doesn't exist, it could be an asymptote, could be a spike like this. And in this case, we did have a minimum, which was a critical point. In the case of 1 over x, where the asymptote is, obviously, we cannot have a point there. So the procedure to find min and max, right, the locations, which we call like extrema, the procedure is to take the derivative and set that derivative equal to 0. Now, does anyone remember why we have to set it equal to 0? Why are we setting the derivative equal to 0? The tangent line that goes through the min and the max has the slope of 0. Tangent line. That's the concept, guys, for the test that you need for the next week. The tangent line, the tangent line, the tangent line. Everything's about tangent line, right? We have a function, and the tangent line slope is m equal to 0. What was the calculation for this? You have your f of x, then you take the f prime of x, but then when you plug in the value here, x equals a, you get m equals f prime computed at a value a. Well, this m is now 0. And you can see that you have an equation to solve, right? You have an equation to solve. So for every max, min value, whatever, right? We have the horizontal tangent line where slope m is equal to 0, and we know m is the derivative computed at value a, which is the reason we say you set derivative equal to 0. You don't have to worry about set derivative equal to 0. You know that the slope is 0, so that's why we are equaling the derivative to 0, because we are looking for all of the points where the slope has 0 value. So where we have what we call horizontal tangents. So consider a function y equal sine x. Do we have min and max on this one? Yes. How many? Infinitely many. What are those? So, to find the answer, we take the derivative, which is cosine x. We set that equal to 0, and we solve this equation. Where is the cosine x equal to 0? Cosine x is equal to 0 at every pi over 2 plus minus 2n pi. N is 0, 1, 2, 3, and so on. There are infinitely many. So all of these critical numbers. So if you know your trig well, your trig graphs, as your pi over 2, as your 3 pi over 2, as your 5 pi over 2, there's a negative pi over 2, there's a negative 3 pi over 2. You can see that every single max and every single min that you see are on this pile over here. Oh yeah, plus n pi. Yeah. Plus n pi. You're right. I would find it now when I start checking. So pi over 2, if n is equal to 0, this drops, and you just have this one. If n is equal to 1, and this is when I would find it, when n is equal to 1, you have pi over 2 plus pi, which is 3 pi over 2 if you do the common denominator. That gives you this minimum. Change n to 2, this becomes 5, right? Because you would have 2 over here. So that's 2 times 2 is 4, plus 1 is 5. So 5 pi over 2 detects this one, and so on. So this equation can detect all min and all max values. And how many do we have? Infinitely many. Which is amazing that you are able to fit infinitely many numbers. Right? Infinitely many solutions in such a simple statement. How about y equal a to the x? Min and a max of this one. Let's do the procedure. What's the procedure? Derivative. What's the derivative of a to the x? And now when you set it equal to 0, what happens? Solve this equation. Come on. What is the solution for this equation? No solution. What does that mean? No min max. Right? No min max. Okay, what else? Does log have min and max?
I have a quick question about for e to the x, it'll like never have a min or a max, it'll always be a solution.
Mm-hmm. Unless I multiply it with something else. It depends. In differential equations, you learn about damped oscillating systems, where the solution is e to the negative, let's say 2x times, say, sine 5x. Well, it should be t, but whatever. And the solution for something like that will be like this. So it has a min, max, min, max, min, max, min, max, and then they die out. So that's possible. What else? Well, I'm not sure why I'm breaking my head. If I can just look at the problems that are given to us and the text. Let's start with 35, which says that the function f of x is equal to x squared square root of x plus 1. Find min max if we have any. So we find the derivative, set it equal to 0, and work out the details. How do I find derivative? What should I do? Product rule. Copy the first, times derivative of the second plus copy the second times derivative of the first. And now we need to clean this up. Remember how I told you simplify, 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 factor? Now we're setting this equal to 0, so we need it. This is going to be x squared divided by 2 square roots of x plus 1 plus 2x times the square root of x plus 1. And at this point, when we set this equal to 0, you see that you can bring one of these to the other side. You have to solve this equation. Welcome to chapter 4. Multiply both sides by 2 square root x plus 1, and we get x squared is equal to negative 4x times x plus 1, because root times root cancels. So I have x squared is equal to negative 4x squared minus 4x. When I plug everything on a pile, I get 5x squared plus 4x equal to 0. Factor it. And finally we have x equals 0 and x equals negative 4/5. And that's it. You have two critical numbers. Plug those back in the original equation. So f of 0 is 0 squared square root of 0 plus 1, which is 0. Gives us the first critical point, 0, 0. And then f of negative 4/5 is negative 4/5 squared times the square root of negative 4/5 plus 1. So that's 16 over 25 times the square root of, and over here, when I put the 5, it's 1/5. Right? Because 1 is 5 over 5. 5 over 5 minus 4 over 5 is 1 over 5. So I have the second coordinate, well, second point, which is negative 4/5, and then 16 over 25 root 1/5. And those are critical points. So critical points. So this is what we have for calculation. And now there's one more piece to this lecture. What this detects, these derivatives, they detect on the function that goes infinitely left, infinitely right. It detects minima and maxima inside that interval. But when you have a finite line that has the beginning and the end, derivative does not detect endpoints as min and a max. So, if I draw a function like this with the arrows, that's infinite. But if you draw a function like this with its dots, that's finite. And that one is from x equals a to x equals b. It's on the closed interval. We call the closed interval a to b with the brackets. Now infinite one is negative infinity to positive infinity using parentheses. You can also use the double bar r. Whatever notation. So now, in addition to doing the derivative to check for all of the infinity points between A and B, to find all the min and max values you can find. You also have to calculate function value at A and B and make sure, right, to actually find out whether absolute max or absolute min occurs at those endpoints. Let me give you graphical examples for this. You see, I understand that there is a max and a min, right? There's a max here, which is a relative max, and there's also another relative min. But this one over here is the absolute min. And this one over here is the absolute max. And as you can see, it's endpoints. They're finite. There's a dot at the end. It's finite. So now they become the part of the game. These ones we detect using f prime of x equals 0. The endpoint ones we have to compute and compare them to the ones we found through the derivative. Now, why do I have to compare them to the ones I found in the derivative? Well, consider this. You see now the derivative one is the ABS max, and the one that you compute at the endpoint is relative. Over here they're reversed. You can have this to be taller peak than down, right? So you have to find derivative and the y values, so critical points first, and then you have to find the endpoints, and then you put them all together. So let's take a look at the problem. Absolute minima and maxima, they give us some cute problems here. Let's find something that it's not too pretty. No coughing. Sheesh. F of x is equal to x divided by, open parenthesis, x squared plus 3, everything squared, and we are supposed to compute that on the interval -2 to 2. So guys, these are your a and b on the interval. They're not x and y, they are x and x. It's the interval on x-axis, like interval of time from 1 to 3 p.m. It's not from 1 p.m. through range. Makes no sense. Has to be same concept if you have an interval. Right? Interval has the same units and same dimension. So what do? We crack the derivative, right? When you're done with the derivative, set it equal to 0. That will detect all the internal stuff, and then we plug -2 and 2 in the original equation, figure out those, and we're done. So what's the derivative? Oh, I see how it is. Logarithmic differentiation didn't go too hot, huh? So copy the problem as is. And then x, so it's 1 over x minus 2 times x squared plus 3, and then, so that's going to be 4x. Delete this 2. There you go. Now we set this equal to 0. You have this situation. So if you have this situation, what you do is you set each one of these to 0. So x over x squared plus 3 squared equal to 0. When you cross multiply, right? You get x equal to 0. And now to find y, you go f of 0 equals to, and you have 0 over 9, which is 0. So you have the first point, 0, 0. You don't know what it is. Let's chill. We have more stuff to solve. The second part needs to be solved. So we set that one equal to 0 as well. Move to the other side. Cross multiply again. And move, I don't know, everything to the right. So move these two terms to the right. We get 4x squared minus 1x squared is 3x squared minus 3 equal to 0. Factor out 3. Whoo! We got 1 and negative 1. Beautiful. Calculate f of 1. It's going to be 1 over, where was that? 1 plus 3 or 3? X squared plus 3, right? So 1 plus 3, everything squared. The whole thing works out to be 1 over 16. So another point we are calculating is 1 over 16. Negative 1. So negative 1 over negative 1 plus 3 squared is negative 1 over 4. So negative 1, negative quarter. We have 3 critical points just by solving the equation. So we look again. We have the function. We find its derivative using logarithmic differentiation. Guys, if you like pain, go ahead, use your chain rules and product rules and quotient rules for problems that can be done in one step. Then we set each one of the factors to 0. That's the 0 product rule. And solve all of those equations. We obtain these 3 points. And here's now the new stuff. We compute f of 2, which is going to be 2 squared plus 3, everything squared. It's 2 over 49. So that gives us additional point 2 over 49. And we also compute f of negative 2. So these are your A and B. Right, this is your A, and it's your B from the interval. Now negative 2, you have, oh, I have a mistake up there. No one caught that one. No one caught the mistake before, right? This one. This one is squared. So it's still 1 over 16, but it's negative. Because negative 1 squared is positive 1 plus 3 is 4. 4 squared is 16. So it's negative 1 over 16. All right. I have 5 points. I have 5 points. Well, one of those has the highest y value, and it should be common sense that that is the absolute max. And one of them has the lowest minimum y value, right, which will be a minimum, and that will be an absolute min. So we are looking for the largest positive number. Well, 0, 0 is in the middle of everything, so no one cares about that. We are looking at all the y values. We want to pick the highest number, and that's absolute max point, and the lowest number on the y-axis is where the minimum, absolute minimum is. So now what's bigger? negative 1 over 16 or 2 over 49? Which one is bigger? 1 over 16. Yep. So here's your ABS max, and again you have negative 1 over 16, and this is your ABX min. ABS. So the procedure for this is to deal with the inside first by setting the derivative to 0 and considering if the function is not differentiable like absolute value of x. So do that first, and then at the end of the after you're done with that, you calculate the y values at endpoints, and you simply compare. You look at the list, which could have 3 numbers, it could have 50 numbers. You look at that list and you pick the highest number, that's where the absolute max is, and the lowest number, which is the absolute min. That's it. I hope you're not disappointed. That's 4.1.